Electric potential or voltage. Our study of electricity began with Coulomb's law, which calculated the electric force between two charges, big Q and little q. By assuming Q was a small positive charge and dividing F by Q, the electric field due to the charge Q was defined. By calculating the work done by the external force in a system of charges, or the negative of the work done by the electric field, electric potential energy was defined. Just like we did in defining the electric field, we'll divide the electric potential energy by Q, and we'll get the electric potential, also called voltage V. Electric potential, or voltage, V, is measured in volts. As was done with the definition of the electric field, the system that was required to define electric potential energy, two objects or a field in an object, was removed. Electric potential is a property of the space surrounding a charge Q, just like the electric field is a property of space surrounding a charge Q. But the electric field is a vector field, right? Magnitude and direction. And the electric potential is a scalar field. There's no sense of direction. And here's the voltage, or the electric potential. Electric potential and voltage, although not always exactly the same, they can be used interchangeably in this course. Electric force, electric field, electric potential energy, and electric potential have all been described. Here's a handy chart to remember the relationships. We started with electric force, we lost a Q, and we became electric field. And both of those are vectors. Then we went down the table, and you lose an R. So you went from electric field, and we defined electric potential energy, but we lost an R there. So that's potential energy is KQQ over R. And then we went over to electric potential, and we lost one of the Q's. So we have voltage is KQ over R. And these two quantities on the second row are both scalars. Voltage can be thought of as the electric potential energy per charge, which is expressed as joules per coulomb. Hence, 1 volt is a joule per coulomb. To make this more understandable, a volt is visualized as a battery adding 1 joule of energy to every coulomb of charge that goes through the battery. Like electric potential energy, voltage is not a vector, so multiple voltages can be added directly, taking into account the positive or negative sign. Like gravitational potential energy, voltage is not an absolute value. It is compared to a reference level. By assuming a reference level where V is equal to 0, as we do when the distance from the charge generating the voltage is infinity, it is allowable to assign a specific value to V in calculations. The next slide will continue the gravitational analogy to help understand this concept. Here's a topographic map, and it has all these lines in there. Each line represents the same height above sea level value. The area between the lines represents the change between heights. A big space between lines indicates a slow change in height, so that would be over in this area. A little space between lines means there is a very quick change in height. Up here, over in here, maybe over here also. Where in this picture is the steepest change in height or incline? The steepest incline on the map on the previous slide was at Keith's Dome. That's where the lines were closest together. The topography lines are called equipotential lines when we use them to represent the electric potential. They represent lines where the electric potential is the same. Just like on the topographic maps, the line showed you where the height above sea level was the same. The closer the lines, the faster the change in voltage. And the bigger the change in voltage, the greater the electric field. Let's look at this charge here, plus Q. The direction of the electric field lines in blue are always perpendicular to the equipotential lines, which are in green. The equipotential lines are places in space where the electric potential is the same. It's the same voltage. The equipotential lines form concentric circles about a charge, since the potential V is inversely proportional to R, the distance from the charge. The potential is equal at all points on a given circle. The equipotential lines nearer the charge are at a higher magnitude of potential and are positive. The electric field lines point in the direction of decreasing potential, right? Because out here the potential is 0. A negative charge would be surrounded by negative equipotential lines, which would also go to 0 and infinity. More interesting equipotential lines, like the topographic lines on a map, are generated by more complex charge configurations. Now let's consider the negative charge. The equipotential lines are lines of constant negative voltage. The equipotential lines nearer the charge are at a higher magnitude of potential. The electric field lines point in the direction of decreasing electric potential. The potential at infinity is 0, so the potential near the charge, right near the charge, is a very large negative value. So the electric field lines are pointing in the direction of decreasing potential. Higher magnitude perhaps, but because of the negative side, it's a smaller potential. What is the electric potential, or voltage, 25 centimeters from a 5 microcoulomb point charge? Start by converting microcoulombs to coulombs and centimeters to meters. Then use the electric potential equation, plug in Coulomb's constant, here's our charge, here's the distance away, and you get 1.8 times 10 to the 5th volts. What is the electric potential 50 centimeters away from a minus 7.4 microcoulomb point charge? We have our equation for voltage or electric potential. Substitute in the numbers, make sure you carry the negative sign here, and you get a negative 1.3 times 10 to the 5th volts.